Welcome to Teaching with Technology in Undergraduate Mathematics. My name's Ami Mamolo, and you're tuning into choosing and using online teaching materials. I'm speaking with Kitty Yan and Sheree Rodney, who are here to help synthesize key ideas from Activity 2, Dynamic Modeling and Visualization in Calculus. This activity explored applets made with dynamic geometry software for the purpose of teaching Taylor series expansion. To start things off, could you two tell us a bit about how these applets can benefit student learning?
Sure, Amy. Using DGS such as GeoGebra and GSP makes it easy to transition from concrete representation to numeric abstract symbolization. Learning takes place in various ways for different people. While some learn through abstract symbolism, others require visuals to examine properties and relationships between objects. For example, using DGS with Taylor series expansion, a slider is provided with which you may vary the value of n. As you drag the slider, you see the Taylor series plot smooths itself along the curve, which would not be possible had it been done in static environment. The opaque algebraic expression becomes a transparent and eventually friendly object through graphing and dynamic visualization. You see, the beauty about this is that not only is the concrete to abstract representation possible, but also with dynamic visualization, we can actually see both the algebraic and the geometric representations on the screen at the same time. That is, you'll see the shape as well as the symbolic expression that it represents while dragging is done.
That's right, Sheree. What we could see in the applets is the immediate changes of the graphs as the depths increase in GSP or as the slider changes in GeoGebra. Taylor expansion is a good topic because, first of all, it is an infinite sum. This cannot be achieved through calculations by hand. You may ask students to find the Taylor series of a function up to terms of, say, degree 3 or 4. For higher degrees, it's difficult and cumbersome to compute. Without a dynamic visual demonstration or animation, students don't quite get empirical evidence that the accuracy of the approximation increases when the number of terms increases. For this very reason, doing calculations by hand comes procedural and meaningless. Students need a clear picture of where they're at and where they're heading to.
For someone who's new to teaching with dynamic geometry software, what do they need to be thinking about when planning their lesson?
Well, research in mathematics education suggests that, in general, for integrating technology as a teaching aid, there are 4 aspects needed to be considered. First of all, the user, your students. Which student population are you engaging with? How they will access or view the content, and what content they would really benefit from seeing done this way. The other aspect is the features of the content to be displayed. Is it finite or infinite? Is it graphical or symbolic? The other aspect is the context of use. Is it used to introduce a concept, introduce an application, or invite students for investigation? And lastly, we need to consider what learning objectives we want to achieve with a particular applet visualization. Taking the Taylor activity as an example, the learning objective is to deepen students' understanding of increased accuracy of approximations of a Taylor expansion through DGS.
Instructors can also think about the accessibility of these applets. For example, GeoGebra and GSP are both free and easily accessible. They can be integrated into lessons without much prior experience. Also, ready-made applets can be used to target a variety of mathematical concepts at the undergraduate level. They can be used to demonstrate ideas in a lesson, or students can use them to experiment with mathematics. These applets give students opportunities to view or engage with mathematics in different ways, and from different perspectives. So, as an instructor, you can use the same applets with tailored questions to differentiate instructions, basically, to diversify your lessons. Take, for example, if students are really struggling with lecture material, you may invite them to play with the applets outside of the classroom and verbalize what they see. You can then extend the learning by asking more sophisticated questions, such as, what would you expect to see if I change one of the features of the applet? Or, how could you extend this idea?
These are great questions, Sheree. In the Taylor series applets, we could also ask questions such as, what if we change expansion points? What if a function is poorly approximated at some arbitrary point? And what if you were asked to find the best approximation for arctan as x approaches infinity?
Those are all great questions, but I do wonder, does DGS take away the need to do the computations? Kitty, you mentioned before that doing calculations by hand can become procedural and meaningless. Don't we want students to be able to compute Taylor series?
Yes, absolutely. Approximating functions with a Taylor expansion is a key technique in calculus. Spending time helping students see how this technique works and how the approximations get better is important to working with functions. The DGS approach doesn't take away from students doing the computation, but rather it adds a visual confirmation that helps explain what the computations are all about. As I mentioned earlier, without a dynamic visual demonstration or animation, students don't quite get empirical evidence of the accuracy of approximations. With DGS, they do.
Definitely, Kitty. Computational fluency is important. We don't want to take away from that, but what I would like to add is that the dynamic visual approach invites students to observe and notice changes and relationships, to seek variance and invariance, and ask why a particular property is preserved. During a lecture, an instructor could pose deliberate questions to direct students' attention to the key properties or ideas embedded in the applet, which is important for strengthening students' understanding of what they see. For example, the dragging tool and the slider feature in GSP and GeoGebra respectively make dynamic changes visible and therefore evoke a sense of understanding of covariation by seeing that as the dependent variable changes, the independent variable changes also.
It sounds like DGS could be widely applicable and useful for many topics, particularly ones that students struggle with or that are especially important to build on. Is that fair to say?
Yes, Amy. There are lots of other good topics that can be enhanced through dynamic software, such as derivatives, integrals, and computing volumes. The Calculus in Motion website offers lots of apps on these topics. They're all constructed with Geometry Sketchpad. Another good topic I can think of is linear approximation, Newton's method, for example. There is no shortage of GeoGebra apps that demonstrate this topic.
Note that we're not implying here that there is no value in static diagrams. In fact, a static diagram can also offer a concrete representation, but it has limitations because it can only represent one moment in time. Whereas with the dynamic diagram, you can use the animation feature to demonstrate change in real time. That is, dynamic visualization provides the potential to show continuous motion where the entire object remains coherent as you use the slider to manipulate the object. This shows a clear dependency between the attributes of the object. For example, in Taylor expansion, as the value of the approximation changes, when each term is added, the constructed object, the graph, remains intact.
Yes, just to add to Sheree's point about how dynamic visualization allows events to be observed in real time, this is made possible by the animation features on the DGS. And the possibilities don't end with two-dimensional representations. In GeoGebra, any object created in the 3D graphics view also has an algebraic representation in the algebra view. This allows students to switch from one type of representation to another readily and seamlessly. In fact, students' abilities to switch amongst representations is an important part of their mathematical literacy and fluency. They need to understand what they're computing, and they need to see the implications of their computations. Having the multiple representations available on one screen supports this aspect of students' understanding.
This brings us to the end of our synthesis of Activity 2, Dynamic Modeling and Visualization in Calculus. Thinking back over our conversation, what stands out for me is that dynamic visualization can promote a direct connection between the student and the mathematical object, which can make it easier to transition from concrete representations to numeric abstract symbolization. And importantly, for anyone starting out using DGS, when choosing an applet, consideration should be given to what learning objectives you want to achieve and what features of the applet will best support these objectives. You also need to think about how your students will use the technology and when to integrate it in a lesson. We hope you've enjoyed exploring these ideas with us. To learn more about how DGS can be used to extend teaching and learning opportunities for students, be sure to check out our module, Dynamic Experiences to Support Student Reasoning and Proof. Thank you, Kitty and Sheree, for joining me today. I'm Ami Mamolo, and I want to thank you very much for tuning in to Teaching with Technology in Undergraduate Mathematics.